Okay, so this is going to really hopefully review the exponential functions graphing that we started. So just as a reminder, an exponential function is a function that has the variable in the exponent location, and it often takes this form, like right here. And so I just want to take a minute and start off by looking at each of the different transformations on our parent function. So let's just draw our parent function, and I'm just going to say this is y equals b to the x. And so we know that that's going to have a y-intercept of 0, 1, because when you plug 0 in for x here, anything to the 0 power is 1. So it doesn't matter what our base is, we're going to have that power of 1. And then our exponential growth graph looks something like this. And one of the features of an exponential growth graph that we've talked about is that it has something called an asymptote, which we can draw in with a dotted line. And that line would be at y equals 0. And that asymptote is the line that as x gets really, 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 really small, it's going to approach this line. It's never going to quite reach it, because if you think about taking something and having it over and over and over again, a half, a fourth, an eighth, a 16th, 1 over 32, 1 over 64. It's getting really, really small, but it's never going to quite reach that 0. And that's what's happening as our numbers get really, really, really small. We end up, as our x values get really, really, really small, our y values are approaching 0. So we have this asymptote at y equals 0. We have this y-intercept at 0, 1. But those things can be affected by the transformations on our graph. So we're going to start out by looking at the k value. And so the k value is what shifts the graph up or down. And so I want us to just think about what that graph could look like. That could mean that if the graph shifted, if that said something like a times b to the x minus h, let's say it said plus 3, that would mean that everything shifts up 3, including our asymptote. So our asymptote would now be here at 3. We'd have a y-intercept at 4, and the whole graph just shifted up 3. We also might have something where it says something like minus 5. Same idea, except now it's going to shift down 5. So our asymptote also shifts down 5. And then that whole graph shifts down 5 as well. So that's that k value, shifting it up or down. Then we also have the h value. And so let's think about what h is going to do to it. The h, let's say we have this graph, regardless of what a, b, or k are. That is going to shift it either left or right. And so in this example, that x minus 3, because the formatting is x minus h, h is just a positive 3 because that minus is already there as a part of the formula. So it's going to shift it to the right 3. So this graph that was originally there is going to shift to the right a little bit. And it's really hard to see, but if you envision that graph, that same point that's here is now shifted to the right 3. The asymptote didn't end up changing at all, right? Because if we're shifting it horizontally, it's not going to change. And then let's say we have a graph that says y equals a times b to the x plus 2. That's actually going to shift it to the left 2. So that 0, 1 original y-intercept gets shifted over to the left. Again, it does not change that asymptote. Okay, and then let's take a look at the a value. The a value is what does a vertical stretch or compress, which means what it's affecting in this graph is the steepness of this graph. It also means that if we have a negative a value, it will be reflected. So that would look like this, right? That asymptote is still in the same spot, but now it's going from the asymptote. Everything is below the asymptote. It's approaching from below instead of approaching from above. The other thing that the a value is going to affect is it is going to affect the y-intercept. So when we think about just a regular graph, let's assume there's no vertical shift. If we just have y equals 2 to the x, that graph is always going to have a y-intercept of 0, 1. Because when we plug in 0, it doesn't matter what that base is. Anything to the 0 power is 1. But now, if we say it's 4 times 2 to the 0, now our y-intercept is 4, right? Because 4 times 1 is 4. So that a value is going to have an impact on the y-intercept, just like the k value also would if it shifts it up or down. So both the k and the a value are impacting the y-intercept here. And then last but not least is going to be the base right here. And the base is going to affect how quickly that graph grows. So if you remember, we looked at all the different graphs and we said 2 to the x looked something like this. And then 3 to the x looked something like this. And then 4 to the x looked something like this. And so on. They all had that same y-intercept of 0, 1 here. But if as the base got bigger, the more quickly we experienced that exponential growth. So that rate of change is larger. So that is just a summary of how our transformations are affecting our exponential growth graphs. And just a reminder that these letters, they're not new, right? The A value is the vertical stretch or compress. That was in our quadratics unit. That was in our radicals unit. That was something we saw in our polynomials unit. Same thing with this minus h shifting it left to right and this plus k shifting it up or down. We saw those in those units as well. Now let's take a look at this slide from your homework in Desmos. And I know that we had some questions and I wanted to talk through how we might have figured this out. So when I'm looking at this, I might notice that there's only one kind of transformation that is going to be able to affect the asymptote. And you might notice that we have a couple of items here that reference where that asymptote is. And so the only thing when we are considering y equals a times b to the x minus h plus k, the only thing that's going to affect that asymptote is the plus k, the shift up or down. So when I look at that, I want to say, oh, well, if the horizontal asymptote has moved to y equals -1, that means there had to be a shift down to make that happen. So I can go ahead and match y equals -1 with y equals, the horizontal asymptote of y equals -1 with y equals -2 times 100 to the x minus 1. And then same thing here, I can also identify that this that has a shift of positive 50 must have that horizontal asymptote at y equals 50. And then where it says horizontal asymptote along the x-axis, we know that that must mean that the horizontal asymptote is at 0 here. So there must be no shift up or down. So that puts this one matched with this one here. Then we look at some of the other things it says. So for example, I see exponential growth factor of 2. And when I look at these, this one is the one that has a base of 2, whereas this has a base of 1/2, this has a base of 100. So we can also match this one with the with the 100 times 2 to the x. We see exponential decay factor of 1/2. Well, there's that decay factor of 1/2. So that goes with our pink group. And then the y values are all below the x-axis. That has to mean that it is flipped like this so that it's all below that asymptote. So the part of our equation that would flip it like that would be a negative a value. So when we look at our different equations, that has a positive a value, that has a positive a value, this one has a negative a value. So that must match and have all the y values be below the x-axis. Here's another example from our activity. And so when we look at this, one thing we might notice is that this graph is reflected facing downward. So what that tells me is that we only have 2 that have negative a values. So that eliminates these 2 choices because it has to have a negative a value to be reflected downward like this. Then I also noticed that the rest of this part is all the same. So we're just looking at whether it's -3 or -1/3. And you might be able to have a sense of why, which one you think it is. But a good way to check is to go ahead and check that y-intercept. Because when I plug in 0 for x here, I'm going to get -3 plus 4, which is 1, which tells me that in this equation, the y-intercept is 1. If I plug in 0 here, I'm going to get 3 2/3, which tells me that my y-intercept would be 0, 3 2/3. So when I look at this graph, this y-intercept is clearly at 0, 1. So that means that this has to be the right answer. So in this slide, you were asked to match each equation to its graph. So as I start out, I just look at any one graph. So let's say I'm looking at this graph right here. I see that it's reflected downward. So I have to be talking about either this one right here or this one right here, because they're the only 2 that have a negative a value. But this one that I have here is also shifted up 5. But when I look at this graph, it definitely does not look as if it's shifted up 5. So it's got to go with this equation right here. So let's see what else we have. We have another one that is reflected downward, and this one is shifted up 5. So that one must match with this one right here. Then I see that we have, let's see, 2 graphs right here that both look like they are exponential decay, which means they have to have a base that is a fraction. So like this one has a base of 1/2, this one has a base of 1/2, this one has a base of 1/2. So those are the 3 that are decay graphs because they have a base that is between 0 and 1. So it has to be less than 1 to be exponential decay. And so this one is shifted up 5, but neither of my graphs look like they're shifted up 5. This one's shifted down 5, and this one does look like it's shifted down 5, so those two go together. And then this one is not shifted at all, so it just goes with the equation that has k equals 0. And then we have one more graph to match, and it is exponential growth, so it can't be this equation right here. So it's got to be one of these two. And because it's not shifted up 5, the asymptote is at 0, it's got to go with this one right here. We're going to go ahead and look at 2 more from the Desmos homework. So this one said settle a dispute, and it said that Mark thinks the equation y equals 4 to the x will match the solid graph. Mia thinks it will match the dotted graph. Who is correct? So an easy way to start off is to notice that Mark and Mia's graphs have different y-intercepts. So if I look at the equation y equals 4 to the x, and I plug in 0 for x, that should give me my y-intercept. So 4 to the 0 is 1, which means that only Mark's graph has the correct y-intercept because Mia's y-intercept is 4. So it can't be Mia's graph. But before I decide for sure that it's Mark's graph, I might want to check at least one more point. So if I plug in 1 for x, that tells me that when x is 1, y should be equal to 4. But if I look at Mark's graph, he has when x is 1, y is equal to 3. So that tells me that neither of these graphs are correct. So I could explain my thinking there. The other one I want to look at is this one. And as we're trying to figure out which equation of this graph is shown, one of the things I might start off by doing is rewriting this bottom one, because the format that we're used to seeing is the k being written at the end. So I might just rewrite it like this. And as I recognize that that plus 3 is the k, I know that that can't be right for this equation, for this graph, because I don't have a shift up of 3. That asymptote is definitely at 0. So that brings it down to the other 3 options. I also see that I have a y-intercept here of 3. So when I think about plugging in 0 for x, this one won't give me a y-intercept of 3. It'll give me a y-intercept of 2. So that one can't work. And then I have a feeling that it can't be this y equals 3 times 6 to the x, because I feel like that's going to be too big or too steep. 6 might be too steep, but we can check by plugging in 1. If I plug in 1 for x, I should get, 1 is right here. I should get 6. But if I plug in 1 here, I'm going to get 6 times 3, which is 18, and that is too steep. So if I check here, when I plug in 1 for x, I get 2 to the first is 2 times 3 is 6. So I do get that point. So that makes my answer this top one right here. So one of the things I want you to know is that as you were doing some of these activities, it is totally normal to be doing some process of elimination, some guess and check kind of thinking where you say to yourself, I know it needs to be more steep, but is it going to be 5 or is it going to be 6? I know that it needs to be a bigger shift up, but what exactly is that shift going to be? So there is some elements of process of elimination or kind of some guess and check, but you should have enough understanding of the transformations to make sure that you're going in the right direction, to say, oh, I need to go even bigger because my number is still not steep enough. So those are kind of where you should be right now with your understanding of exponential functions and their graphs and transformations. So exponential functions are everywhere in the world, and so we're going to look at just a couple of examples right now. So when you have a real life quantity that is increasing by a fixed percentage each year, it's going to follow the format or the equation y equals a times 1 plus r to the t, where a is that initial amount, which makes sense because the initial amount is when no time has passed. So when t is 0, right? That's the y-intercept. R is going to be your percent increase written as a decimal. And then we call 1 plus r the growth factor. And then t is the amount of time periods that have passed. So let's look at an example. So in this example, it says that in 1996, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by about 92% each year. And so we're going to write a growth model giving the number n of incidents t years after 1996. So as we are writing this model, it's going to be in this format. And so when we do this, we need to know where we're starting off. When time is equal to 0, when no years have passed, it's 1996. And it tells us that there were 2,573 incidents. So that's going to be my A value because that's what happens when no time has passed. Then my rate is going to be the percentage written as a decimal. So 92% is 0.92. And the reason why it's 1 plus 0.92 is if we had just 0.92, that would say that we would have 92% of what we had before, which would be decreasing in the number of viruses. But we have to make sure we represent that we have 100% of what we had before plus 92% more, right? We are growing. So that's why it has to be that 1 plus 0.92. And then we have to the power of t, which is our number of years that have passed. And so here's our model, and we want to know how many incidents were there in 2003, which is after 7 years have passed, which is 247,484 if we round to the nearest whole number. So that is how many viruses there were in 2003. So let's look at another example. This one says that in 1970, the population of Kern County, California was about 330,000. From 1970 to 2000, the population grew at an average annual rate of 2.4%. So we're going to write an equation that will be the population. And so my starting value, or my initial value when no time has passed, is that 330,000. That's when we're in 1970, when t equals 0. And then my rate is going to be 2.4% written as a decimal, so that's 0.024. And so I get this model for our population to be 1.024 to the t times that 330,000. And so we want to plug in 20 because 20 years have gone by in 1990. And we get 530,289.5 something. And so we have to ask ourselves, in 1990, do we have that half of a person? And the answer is no. We don't have a half of a person. We can't round a half of a person into a whole person. That half person doesn't exist. So even though 0.5 is usually a round up situation, we are not going to round up because we can't count that half of a person as as a whole person. So we have 530,289 people in 1990.